Hello friends, I'm Arpan. Welcome to my channel Scientific Study. Today we are diving into the quantum computer. This is second part. If you didn't check out previous part, I recommend to check out for introduction of quantum computer. Let's start. Quantum computers are mind-blowing. But have you ever wondered what makes them so powerful? Unlike classical computers that use simple 0 south and 1 south, quantum computers operate on something entirely different, qubits. And to control qubits, we need something special, quantum gates. In this video, we're going deep into the world of quantum computing. You'll learn about qubits, quantum superposition, entanglement, and the quantum gates that make all of this work. By the end, you'll have a strong understanding of how quantum computers process information in a way classical computers never could. Let's dive in. A qubit quantum bit is the fundamental unit of quantum computing. It's similar to a classical bit, but with one massive difference. It doesn't have to be just 0 or 1. Thanks to a quantum property called superposition, a qubit can exist in both states at the same time. Now, why is this important? Let's compare it to classical computers. A classical bit can store either 0 or 1 at a time. A qubit can store 0 and 1 simultaneously, allowing quantum computers to process multiple possibilities at once. This is why quantum computers have the potential to solve problems that would take classical computers millions of years in just seconds. Now, let's talk about another mind-blowing property of qubits, entanglement. Entanglement is when two qubits become linked, meaning that whatever happens to one instantly affects the other, no matter how far apart they are. This is not just science fiction, it's been proven experimentally. In fact, entanglement is what makes quantum computers exponentially more powerful than classical computers. Example, imagine two entangled qubits. If you measure one as 0, the other instantly becomes 1, no matter if they're millions of miles apart. This instant communication property is why quantum computing is so revolutionary. Just like classical computers use logic gates or not to process information, quantum computers use quantum gates to manipulate qubits. But unlike classical gates, quantum gates don't just flip 0 south and 1 south. They perform complex transformations on qubits. Let's break down some of the most important quantum gates. Hadamard gate H puts a qubit into superposition, both 0 and 1. Pauli gates X, Y, Z rotates qubit states in different directions. Sihanouk gate entangles two qubits, allowing them to act as a single system. T and S gates are just phase for interference-based quantum computations. These gates form the building blocks of quantum circuits, allowing us to create powerful quantum algorithms. Now that we understand qubits and quantum gates, let's talk about why they are so important. Quantum computers using these concepts can revolutionize industries like cryptography and cybersecurity, creating unbreakable encryption, molecular simulation, designing new drugs and materials, artificial intelligence and machine learning, supercharging AI models, optimization and logistics, solving real-world problems exponentially faster. For example, Google's quantum computer Sycamore solved a problem in 200 seconds that would take the world's most powerful supercomputer 10,000 years. That's how powerful quantum computing can be. Now that you understand qubits and quantum gates, it's time to go deeper. In the next video, we'll build quantum circuits and explore quantum algorithms that power real-world applications. So if you're excited about the future of quantum computing, subscribe to QSnap, hit that like button, and turn on notifications so you don't miss the next episode.